Okay, well, good morning, everyone. Today we're going to hopefully finish off the section called 5.2, the definite integral, and then we'll finally get to see today the shortcut method, which will allow us to find the exact area under a curve without doing any numerical estimations or sigmas or any of that kind of stuff. So that's a kind of nice point to get to. But I've still got a few things I want to talk about in the definite integral ones. So I'm just going to go through some situations that we have. Right, the first one, we're going to look at how you can find the area under a curve when you're given a graph. And we know that you can really only do that if the shape is made up from straight lines or halves of circles, quarters of circles kind of thing. So I'm going to try something a little bit harder, a little bit more awkward. Let's say that's 2. Let's say that's 4. Let's say we do to there, that's 8. And then we go up to here. Oops, we got to here. And I guess I should have drawn it a little bit longer. And this guy is 10. So don't pay any mind to the fact that this isn't really very much to scale, but the gist of what we need is here. So we are being asked to find the area under the curve. So basically that shaded area. And these two are triangles and that's half a circle, which is pretty common. So I'm going to call this piece A, going to call this piece B, going to call this piece here C. And we find the area of each one. And then when we combine them, that will be the area. We have a notation that we use to represent this process, and it looks like this. It's a funny little integral symbol from 0, because that's the start, to an x value of 10, just generic function, whatever it happens to be, dx. So we might be just asked to find this, but what that means is you're trying to find that. Okay, let's see what the area looks like. This is a triangle, 4 units by 2, so that ends up having an area of 4 times 2, half of that is 4. This here is a circle, or I should say half a circle. If you want to get the area of B, don't we need to know what the radius of the circle is first? Okay, looking at that picture, should be pretty obvious, but just tell me what it is anyway. What is the area of that circle?
2.
Yeah. You're all comfortable with from there, if there is 4, so from there to there is 2, right, to either side. So the area of this is half a circle, which is half of pi times 2 squared, which ends up being 2 pi. And I'm coming back to that in a moment. And then the area of C, and this fella is just 2 by 2, and half of 2 by 2 is 2. Now the entire area under the curve from 0 to 10 of this particular function is made up of 4, 2 pi, and 2. But something special about the area of B, because it's below the x-axis, its area is negative, so it's negative 2 pi. So anytime an area is below the x-axis, as it is here, you'll recognize that this represents a negative area, which is totally okay now. It's okay to have negative areas. It has a meaning in some physics situations. So that means that it's this guy, a negative of this guy, and that guy. So the area for this fella would be that. Okay, we're comfortable with this area under the curve. Sometimes bits of it, maybe all of it, can be negative. Second situation is going to be like this. Suppose I told you that the integral from 0 to 1 of x squared dx. Suppose I said, somehow or other, I know the right answer. It's a third. We can use that piece of information to find other areas. For instance, I can use it to find that fella. And it's simply just this guy. So if the curve x squared has an area of a third, if you make it 5x squared, its area is going to be 5 times a third. Its area is going to be 5/3. Suppose I tell you that the integral from 1 to 3 of some function, suppose I tell you that that area is 10. And then I also tell you that from 1 to 3, a different function called g of x, that its area is 3. Then I can use this information, and I can use it to find what the integral from 1 to 3 of 2 times f of x plus 4 times g of x is.
Excuse me, can you scoot the sheet over a little bit?
Is that what you mean?
Yep.
Is that good?
Yep.
Right. Right. Thanks for telling me. I don't really know kind of what you're saying compared to what I get to say. I've got a big wide screen, for instance. Right. If I wanted to find the answer to this after being told that these two pieces of information, what would be the most likely thing you think I'm going to do to make that happen? So don't try and overdo it with weird stuff. Just something very basic that you think would probably do the job. So 2 of these plus 4 of them. How would this help to get this answer? Any volunteers?
2 times 10 plus 4 times 3.
Does that seem reasonable to everybody? 2 of these guys, 2 of 10. 4 of these guys, 4 of 3, right? Add the whole kit and caboodle together, and you now have the answer 32. So far, so good. I can do another, even more unlikely situation. Suppose I tell you the integral from 0 to 1 of f of x is 10. And then I tell you the integral from 1 to 5 of the same function is 20. I should be able to use it to find the answer for the whole integral, the whole area under the curve from 1 to 5. Now don't do anything too sneaky. If you can, and this makes, imagine you started at 0 and you went to 1 and that bit there was 10. And then you went from 1 to 5 and it looked like that, and that bit there was 20. What do you think you need to do to find the integral from 1 to 5 then? I'll take a volunteer.
Would it just be 20?
You add them?
It would be, you're quite right. Now I'll change the question to 0 to 5. And to 0 to 5, which is the question I actually thought I was writing down, what would that one be?
30.
Yeah. Isn't it just the first bit plus the second bit is 30? Oops. So isn't it a bit like if you get 2 bits and you stick them together, that's the area of the whole bit? How about this one? The integral from 1 to 7 of some function is 20. And the integral from 1 to 3 of that function is 7. I should be able to use that to find the integral from 3 to 7. I'll tell you, it's not 27, so think a little bit harder. So from 1 to 7, it's 20, and from 1 to 3, it's 7. So what's 3 to 7 going to be to make this work?
13.
And you do that by taking this guy, take away that guy, and yes, it is 13. Are we looking good? So if I give you pictures, you just find areas and add them all up. If you get information that's written in this way, you basically you take what you've got and you manipulate it to get what you're being asked. Right, let's move on to the last little piece of this, which goes something like this. I wonder what's wrong with my camera. Ah, have I unscrewed it? Will I have to now move back the way again? Can you see both sides of the paper?
Yes.
Yeah, okay. It looks like my camera was a little bit wonky. Can you still see both sides of the paper?
Yep.
Okay, so let me just move this thing a little bit more central for me. Shouldn't change anything because the whole thing's moving. We're still good?
Yep.
Right. Okay, so what's the last thing going to be? I forgot to mention that sigma comes back just for a tiny little bit, but very tiny little bit. Do you know if you find the limit as n tends to infinity of Rn, then that is the area under a curve. Basically, if you take the right-hand side and you do an infinite number of strips, and you add these infinite number of strips up, it's the same thing as the exact area under the curve. Now, that becomes the limit as n tends to infinity of sigma I equals 1 to n of f of xi delta x. So the exact area under a curve, if we were using our delta guy, would be this. So suppose I told you this fella. And x was going from 0 to 2. So if I tell you that the area under the curve is the limit as n tends to infinity of this fella, and we're going from 0 to 2, what would that represent? Well, it would represent 0 to 2. The function you would get from here. So what is going to happen is that you're going to get in a couple of homework questions this guy, and you're being asked to write that guy down. You're not being asked to calculate anything. You're not being asked to go near your calculator. You're just being asked to recognize that this is asking us to find that. So since that is the last thing that we need to do in that section, I'm going to go and show you some examples of that, and hopefully show you that it's actually pretty easy to do. So if you hang in there for a minute, definite integral, view, looking good. Right. I've lost you guys. Oh, there you are, good. Right, so I'm going to go in now and show you that what that looks like. Okay, question 1. Limit as n tends to infinity, the sigma guy, all of this 2 to 4. So it's integral from 2 to 4. And the fella that goes in here is 3x cubed take away 7x. And that's the question finished. So you go 3x, I don't know where that W came from, I must have hit the wrong button in the keyboard. 3x cubed, take away 7x. That's it. So it's a kind of very general algebraic question, but that's all you've been asked to do. I think there's another one. Ah, there is. Okay, seeing this question here, number 5. What number do you think is going to go up there?
7.
That makes sense to me. Okay, it's going to be a little bit messier here, but would you agree that all these xi stuffs, don't all the xi's just turn into x's, and that's pretty much the question over with. So you hit the fraction button, and on the top you do x, and then you click on the bottom. It looks like it's x squared plus 7. So I should be going over here, hitting a little square, and adding a plus 7, and pretty much that's the end of that question. Most of the questions are just like the stuff I've done. Can you see they're, finding areas on curves, or if I tell you something, can you use it to get something else? So that's kind of cool. Although that one there, oh, that one there's kind of cool. Yeah. No, I'll let you worry about that one. That one's got a little kink in it, but that's the only one. So is there anything that I need to go over in section 5.2, which is what we've just finished doing? Do you feel comfortable with that stuff? Any questions? This is us. Then we're on to, we finally made it. We are now going to find how to get the exact area under a curve without having to do a whole load of number crunching or trying to calculate using geometry or whatever. Now, before we can actually do this, I have to get you used to calculating a guy called an antiderivative. Now, when you were doing Calc 1, typically the last section you did was a thing called finding antiderivatives. Does that term seem familiar? Yes, I kind of remember we did some of that.
Yeah.
Right.
Yeah.
Yeah. So let's just recap the issue so that you get used to my way of doing this. Suppose you have a function, f of x, and that function was ax cubed plus 70x plus 10. The antiderivative of this function is typically called, in almost every textbook I've looked at, it's typically called a capital F of x. So the antiderivative of this function is going to be called a capital F of x. So what is it equal to? That's the problem. Well, its name gives you an idea. What you're trying to do is you're trying to find a function for capital F of x, something that goes here. And this function, if you differentiated it, you'd get this guy. So the antiderivative is a function whose derivative would be equal to this. So it's not differentiating a function, it's doing the exact opposite. It's a bit like somebody saying, I just differentiated a function, this is my answer. What was the function I started with? Right? That's kind of what you're doing. So you have to think of the differentiation process in reverse. So let's take each one in turn. If I wanted to get 8x cubed, wouldn't I have to start with x to the 4? Because when you differentiate x to the 4, don't you get x cubed? But how many of these would I need to generate this? Because that would only get me, what, 4x cubed, right? And I need 8x cubed. So I would need 2. Okay, what would I need to start with to get x's? Well, I'd need to start with some x squareds, agreed? But how many x squareds would I need to start with if its derivative ended up being 70x? Well, right, there's a number that needs to go here, right? How many x squareds gives you a derivative of 70x?
35.
35. Now, the derivative is going to be 10. So I need to know what function I need to start with that you would end up with a derivative of 10. And that's probably the easiest of the three, isn't it? 10x. If you ended up with 4, it would be 4x. If you ended up with 20, it would be 20x. This process is called finding the antiderivative. Right? Now, I hope that you've seen this bit where you do a plus c at the end. Have you seen the plus c part? The reason that needs to be here is, couldn't the answer have been plus 4? But when you differentiate plus 4, doesn't it disappear? But it could have been plus 24 or plus 2000 or something else. And so this here is like a placeholder. It's called the arbitrary constant, if you want to know what its name is, for the number that we don't know what it is now, because we only know what the answer to the derivative is, right? We don't know what this number here is because it could have been anything. So that's the placeholder. So to find antiderivatives, I'm going to show you a big table of standard antiderivatives. Okay, so here goes. If you have a function that is like 8x cubed or 70x squared, right? Ax to the n. Its antiderivative, you get it by adding 1 to the power and dividing by the new power. That's sometimes called the power rule. So let's use that as an example. Suppose I wanted to find the antiderivative of this guy. This guy here. You'd add 1 to the power. You then divide by the new power. Can you see that that works? Now check it. Differentiate that. Don't you get this? You know it works. So if you want to find the antiderivative of any power, 5x cubed, 7x to the 4, that kind of thing, add 1 to the power, divide by the new power. So I don't have to keep saying it. Can I just say plus c up here? That way I don't need to keep writing plus c for all the others. Okay, here's a guy. What's the antiderivative of e to the x?
E to the x.
Yeah, I love e to the x because it's the easiest thing in the world to remember, isn't it? Now, let's do some trig ones. They tend to cause problems. What's the antiderivative of cosine x? So basically, what function do you need to start with that when you differentiate it, you end up with cosine x?
Sine?
Yes. Now, the one that tends to cause the most mistakes is the antiderivative of sine x, because the antiderivative of sine x is what?
Negative cosine.
And that's why that one causes trouble, because you are probably really good at differentiation, right? You've done quite a lot of them. And when you differentiate sine x, don't you get cosine x? Have you noticed that when you find the antiderivative of sine x, it's negative cosine x? And what happens when you differentiate cosine? Don't you end up with negative sine? But when you find the antiderivative of cosine, do you see your sine? So what I'm basically saying is, watch out for your trig, because sometimes people make the mistake of making it positive or negative when it should have been the other one, right? So just be careful, because it's a very easy mistake. Those are pretty standard. Now we're going to get to some less common ones. There's a function out there whose derivative is secant squared. What would you need? What's the antiderivative?
Tangent?
Yeah, it's a little bit hesitant, but it is. There's a fair amount of memory required in these standard antiderivatives, right? You just have to have a good memory for them. Here's another, even less common one, but it does happen.
Isn't that like a double angle rule?
Nope. Not
Is
sure what
that
you think.
ln? Yeah, natural
Nope.
log.
Something to do with logarithms?
It's not to do with logarithms, although that one's coming next. I can understand why you think that, but there is a function out there. It's an inverse trig function, if that's a help. Last chance.
Like arcsine or?
Yeah, like that, but arctan, inverse tan. Okay, that might be one that you didn't do very often, but you should have at least a couple of times differentiated someday in that family, right? So an inverse tan. And maybe now that you've seen it, it'll come back to you. Are we looking good? Right. Now, a lot of you said it's something to do with tan, right? So something to do with logs, I should say. This is the guy. What's the antiderivative of 1 over x? Because it does have something to do with logs.
Natural log of x.
Yeah. Now, this isn't a biggie in my world. It's not a biggie. Maybe some professors make a big deal of it. You will see, depending on the context and depending on situations, that sometimes it's written as a natural log of the absolute value of x, and sometimes it's written as a natural log of x. And you might be a little bit concerned about, what the heck's going on here. It's really just to make things mathematically correct. What am I getting at here? You know that you can't find the log of a negative number, agreed? Logs of negative numbers don't exist. And so that there accommodates the fact that if you did 1 over x, if you imagine me doing 1 over x, it looks like that. And as long as x is positive, right, you've got an area under the curve, but isn't 1 over x also get negative x values? So how do you accommodate the fact that x might be negative? Well, you have to stick an absolute value around it to avoid that situation. So how does this work as far as I'm concerned? Even the books are very inconsistent about that. I don't mind if you want to use it, but if you want to use it all the time. I don't mind if you want to use just log of x and say to yourself, I am never going to use this question when x is negative because it doesn't make sense, right? In which case, that's fine. That makes sense to me. If I went and said to you the answer was the square root of x, right? If I said the antiderivative was the square root of x, would you agree you would never use that in a negative x world, right? If x was negative 2, you would never use that, right? And we don't stick absolute values inside square roots to make sure that nobody does that. We just all assume that nobody will do that. So I'm going to go with the don't bother with the absolute value of x. And if the book or the homework sometimes dings you, then stick an absolute value and it'll be happy. But even it doesn't do it all the time. So, it's a kind of sometimes they do it and sometimes they don't. Depends on the context, I guess. Whether the answer could ever be negative. That's a fair lot of things. I'm not finished yet, but I'm kind of getting there. I'm not doing them in any real order, or a little bit of order, but not a lot. I'm doing them more in terms of how rare they are. That one will test you.
That's inverse sine.
Yes. Oh, well done. I wasn't expecting that one to be so quick. Why did that one stick in your head? Because that is a weird one.
Well, I think it's because cosine is a negative one, right?
Yeah. So you just remember that. It's cool. I'm cool with that. Went smooth. I don't expect, but I could be proved wrong. I was proved wrong in the last one, that a lot of you will remember the antiderivative of this guy. But there is a function out there that if you differentiate it, you get this fella.
Cosecant squared, I think.
Oh. Cosecant squared belongs up here and ends up being a negative cotangent. So you were in the right ballpark. It is a trig function, but not the one you said. Anybody want to have a shot at what the antiderivative of a secant tan is? About to do it, last chance. I don't mind you getting it wrong because that's how you learn stuff.
Yeah, is it just secant?
It's just secant. Can you remember differentiating secant? You get secant tan. You remember those guys? Kinda, sort of.
Kinda.
Kinda, right. So that's well, now you've got it. I would keep a version of this list. If you don't see it right now, I do have well, I should have. I know I've got a PDF. I do have a PDF of it in Canvas, so you could just go there and print the thing out. And it's got all the standard antiderivatives that you're likely to come across. Because we are going to use these fellas to get the exact value for the area under a curve. But we needed this kind of information to allow us to proceed. So we are now about to do the shortcut. It's called the fundamental theorem of calculus. Part 2. Sounds like a movie. Right, the fundamental theorem of calculus part 2. Why is it called part 2? Because there's a guy called part 1, which is a bit strange because to me, part 2 is the one that everybody uses, and part 1 is the thing people look at it for 5 minutes and then they never touch it again. So we're going to focus on part 2. What does it say? Well, imagine that you wanted to find the area under a curve called y equals f of x from x equals a to x equals b. And you don't want an estimate, you want to get the exact answer for the area under this curve. Then according to the fundamental theorem of calculus, the area under the curve, right, the integral from a to b of this function is equal to this guy. The antiderivative evaluated at b, take away the antiderivative evaluated at a. Now that's amazing that that's what an antiderivative helps you to find. So the reason why we're doing all these guys over here is because we need to know these things so we can plug them in here. Let's give you a very simple example. Suppose I wanted to know the integral from 1 to 3 of 6x squared. Then this is the way you set up your working. First thing you have to write down is the antiderivative of 6x squared. Now, isn't that add 1 to the power, divide by the new power? So are you okay? Are you comfortable with the fact that the antiderivative is 2x cubed? And then the way you set down the working is you then say from x equals 1 to x equals 3. That's essentially what this bit is. And now you can plug in 3, 2 lots of 3 cubed, take away 2 lots of 1 cubed. So that guy there is basically f of b, and that guy there is basically f of a, but this is the way you set down your working. Right, cubed, 3 cubed, 27, so that's 2 27s is what, 54. 1 cubed is still 1, take away 1. There is the answer, 52. I now know the area under the curve 6x squared from 1 to 3, and the answer would be 52. And that took slightly over 1 minute. Not a strip in sight, not a table with 20 numbers in it, not 10 minutes of boring hitting buttons on my calculator. I mean, isn't that just elegant? The area under a curve is really just dependent on the value of the antiderivative at the start and the finish. That's all you need to know. What's the antiderivative at the start? What's the antiderivative at the finish? Subtract those two guys and boom, that will be the exact area under the curve. Well, let's pick a guy that I like. Right, you recognize that guy as the sine function, even if I don't draw it very nicely, right? Wouldn't it be interesting to know what the area under a sine curve is, right, from at least 0 to pi? So the integral from 0 to pi of sine x dx. Okay. What is the antiderivative of sine x? What is the antiderivative?
Negative cosine x.
Negative cosine x. Then vertical line, x equals 0, x equals pi. This way of writing down the working is almost universal. I don't even, I'm pretty sure I don't know any textbook that doesn't use this. So get used to writing your stuff like this. Now, what do I have? Well, I have negative the cosine of pi, take away negative the cosine of 0. Agreed? Plug it in with pi, plug it in with 0. That's basically your f of b, right? Take away your f of a. Okay, got to be a little bit careful here. What's the cosine of pi?
-1.
-1.
So what we have here is the negative of -1, so that's 1. Isn't the cosine of 0 1, so that's -1. And take away -1 is basically adding 1. Oh. The area from 0 to pi, the area under the curve of the sine function from 0 to pi is actually a really nice number. It's just 2. Which, if you think about it, wouldn't you probably have thought that the answer would have something to do with pi, like 3/4 pi or pi plus a half or something with a pi in it? And it doesn't. It doesn't even have a pi in it. It's just 2. Try another one. I won't draw the picture now because there's too much going on here. Suppose I wanted to know the integral from 1 to 2 of x cubed, take away 2x plus 7. And I've deliberately added one extra thing that we haven't looked at. Okay, so here goes. Antiderivative of each piece. Okay, now the antiderivative of x cubed is going to use the power rule. The power rule says add 1 to the power and divide by the new power. So do you know that if you divide by 4, it's the same as a quarter? Now to double check that, differentiate this. Do you see it works, right? multiply by 4, reduce by 1. We know this is correct. What's the antiderivative of 2x then?
Just be x squared in this case.
In this case, x squared. And the one that we didn't do, although hopefully you'll be able to figure it out, what's the antiderivative of a number, like in this case 7?
7x.
7x. Now you can imagine that the working is going to be a little bit messier now because there's lots of things to do it to. But essentially, I'm going to take all of this and replace it by 2. And then I'm going to take all of this and replace it by 1. So when we plug in 2, it ends up being a quarter 2 to the 4. Take away a 2 squared plus 7, what's it, 2? That's what we get here. And if you plug in 1, I'm just going to be a little bit simpler. Would you agree that 1 to the 4 and 1 squared and 1 on its own is just 1? So isn't this just basically a quarter times 1? Take away 1 squared, add 7 ones. I just didn't bother writing all those 1 cubes and squares and things because, you know, why bother? It's too easy. Now, 2, 4, 8, 16, that ends up being 4, that ends up being 4, that ends up being 14. That guy ends up being what, 6, 6 and a quarter. 6 and a quarter is 25 quarters. This ends up being 14, take away 25 quarters. This ends up being 56 quarters, take away 25 quarters. And this ends up being, oh dear, 31 quarters, I believe. And if any of that's wrong, it's just because I can't count. We don't want these answers to be 7 3/4. We don't even want these answers to be 7.75 or whatever it might be. In calculus in general, we want exact answers, and typically we don't want mixed fractions or decimals unless you can't avoid them, you know, unless there's some other reason that you have to use them. So that's why I had to do that. Now, if fractions are not your friend, or you spend a lot of time in fractions and they cause you hassle, I'm about to try and show you this same calculation, but I'm going to show you how I can let the calculator take some of the workload off me. Right. So suppose I get to here. If you go 14, take away 25 quarters. You see how that answer is a decimal? If you then just hit the math button, where are you? Choice number 1 will turn it into a fraction for you. If you started at this line here, you could probably get away with it. I'm going to try it once. I personally wouldn't do it because there's too many buttons to press and I'd probably screw up. But if you really were desperate, you could go bracket. And then you could go a quarter. Then you'd multiply it by 2 to the 4. Then you take away 2 squared. And then you'd add 7 times 2, and that would be the first one done. Then you'd subtract, and then you do a quarter. And then you subtract 1, and then you add 7. You finish your low bracket, and you get that guy. And then you go math, number 1, and boom, there's your answer. I like to put an extra set of brackets around fractions like a quarter. 90% of the time, it doesn't matter. They work perfectly fine without it. But there are some combinations of multiplications with fractions and numbers that aren't fractions, and it doesn't work. So to show you why I think putting a bracket, an extra bracket around a fraction when you're using your TI-84 is worth it. Suppose it was 1/4 times 2. That's it without a bracket. 1/4 times 2. One quarter times 2. Let's see if I can make it go the other way then. 2 times a quarter. Okay, bad choice. I can't find one where it won't work. I guarantee the first time I stop doing it, I'll have found one where it doesn't work. So I play safe and just put brackets around things. How are we going so far? Is this fundamental theorem of calculus kind of cool? You want to find the area under a curve, you basically find the antiderivative at the start, the antiderivative at the end, and you subtract the two, and you will get the answer. Oh, we can have enough time for this last situation. Do you know sometimes the answer can be negative because there is more of the curve below the x-axis than there is above? Right. Suppose I did this quadratic. What shall I do with this quadratic? I'll make that 0, I'll make that 2. So just double check that. X squared minus 2x. Yeah, okay. That guy there. Suppose I am interested in the integral from 0 to 2. So that fella. Shouldn't this answer be negative? I wonder if the fundamental theorem of calculus copes with this situation. Well, let's find out. What is the antiderivative of x squared? Add 1 to the power, divide by the new power. What's the antiderivative of x squared?
X cubed over 3.
Okay. And then isn't this guy just minus x squared? So there's your antiderivative. Evaluated at 0 and 2. And that becomes 1/3 2 cubed, take away 2 squared, minus, and I do this a lot. 0 seems to be a very common number for these questions. Would you agree that if you plug 0 into here, you just get a big fat 0? So I don't see any benefit in writing down 1/3 0 cubed, take away 0 squared. If you know the answer is going to be 0, you know, just write 0. Now that makes this guy 8/3 take away 4, which is 8/3 take away 12/3, and isn't that nice? Yes, the answer is negative. It's negative 4/3. So that area in there is negative 4/3. Is it possible to get one of these integrals, one of these areas under curves, and get 0 as the answer? Could you get 0 as the overall answer to one of these questions?
If you take the sine function, you could.
Yeah. If you take the sine function, isn't this bit killing that bit and it's 0? You could even get it, I can't draw very well, but can you imagine you had a function where all of that, right, all of this bit here, matched all of this? So pretty much it's not that unusual that you will end up with a 0, and that's okay. And you could end up with negative 4/3, and that's okay. So just trust the math, right? As long as you're doing the math right, the answer will be correct. As long as you're keeping that in your mind. And that's actually a good point for you to say hi. So we're taking attendance now. Okay, there are 2 people missing today. That's not bad. Leah, is it Leah comes this time, doesn't she, or is she my other calc too? You don't know who Leah is, right? She must be my other class then. She was the one that was coming back from Disney World, or Disneyland, or whatever it's called. Okay, 19. Evidently, there's only one person missing. That's me for today. And a couple of people I know are going to hang about because they have some homework questions. But I'll make that an open invitation. If any of you have a homework question that you want me to go over, I'll do that as well. Apart from that, the rest of you, bye-bye. We're halfway through, so my advice is do your homework as much as you are able to so that next week you don't have 2 weeks homework to do in one. It's just better in the long run. And plus it gives you a chance to find out what you don't know, and maybe you can drop in at the end of another day next week and I can help you with your homework situation. Apart from that, bye-bye.
Thanks.
You're welcome. Oops. We must have a lot of people with homework issues. Okay, I'm going to have to kind of do it in order. What might happen if you're really lucky is that the person who's going to ask me is asking me the same homework question that you wanted to know about. So as soon as you get what you were looking for, you just feel free to leave whenever you've done what you need. Okay, so I think Emma's going to be first and Catherine's going to be second, and then the rest of you are going to have to fight for it. Right? So Emma, what's your homework question?
Well, I really had a problem with section 5.1, number 10. It was the midpoint estimate.
Okay, 5.1, number 10, midpoint estimate. So I'm going to go and have a look at that question and see what it looks like. So it takes a little bit longer for mine to load up. Question 10. The one I've got says midpoint 6. Does that look correct to you? It's asking.
I can't see it, but that is it.
Is it? Right. Okay, so let's just double check that, and then I'll use the numbers from that diagram as soon as I can. Here we go. Right, so it's this fella here, right? So this is a velocity against time, and basically you're trying to find the area under this little archway to the x-axis, right to here. And we're going to do M6. So it's going to take me just a few seconds to set up the picture so you can see where I'm doing what I'm doing, right? Okay, so if you can just hang in there for a little while. I'm setting up the information that I need. It's 6, isn't it? Yes. Okay. Right, let's show you how you would essentially tackle this question. Darn it, I need to jump to this one. I think your problem might have happened right at the beginning. See, this would be the typical table. I haven't written down the values, but you can imagine what you'd get from your graph. And if you do your strips, these are the 6 strips that you would probably be using, right? But these are the numbers, right? 5, 10, 15, 20, 25, 30. These are the strips or the numbers that you use if you're doing left or right. But when you're doing midpoints, your table isn't those guys. The first midpoint is actually here at 2.5. And then the second midpoint would be this number, halfway between 5 and 10. And then the next one, and then the fourth one, and then the fifth one, and then finally the last one. So were you using those values to get the velocity? Because these are the numbers that are going to be used to generate the midpoint. Did you do that part?
Yes.
Oh, okay. So that wasn't the mistake. So let's move on to part B, I guess, which is I'm now going to try and estimate what I think those numbers are. And because maybe that's all that went wrong, that your estimate was just a little bit different from theirs. And I can imagine that happening. It's very easy to do that. If I look at 2.5, it's about here. I'm going to call it 17. If I do 7.5, it's about here, so I'm going to call it 27. If you do 12.5, it's about here, I'm going to call it 43. If you do 17.5, it's about 52. If you do 22.5, it's about 58. And if you do 27.5, it's about 60. And I already have a problem. I'm sure that if other people were doing that same list, you might say 26, 28, you might say 42, 44, you know, and so on. Can you see that I'm going to have some differences in numbers? Did you write down numbers sort of as similar to these ones?
Yeah.
Then you didn't do anything wrong there. So the only thing that is left is delta x, which is basically the width of the rectangle, which is still going to be 5 in this case. And then you just add all these numbers up. Now I'm assuming that you added them all up, right, and you multiplied by 5, and you got an answer that looks like that.
That looks like what?
Well, whatever this adds up to is a big number, right? Now, I think you had a decimal in your answer, didn't you?
Yeah.
I'm not sure how you could get a decimal from these numbers or from that 5. So did you do anything in your calculations that involved decimals?
Yeah, I mean, because it said round answer to 2 decimal places, and I really don't know how you could do that. So
You can't in this question. I mean, I don't think anybody in their right mind could read off a diagram anything that's even vaguely close to 2 decimal place accuracy. So I think that's just a bland standard statement that they plug in. Now, if you've done it the way you've said you've done it, and you do it, don't write in those decimals, figure out what this calculation looks like, right? So if you add these all up and times them by 5, I'm guessing the answer's, you know, some number like 820, right? Whatever it really is. Then go for it. And then when you have your third shot, if it then turns around and says it's 815.12, after you've finished screaming, you're going to tell me and I'm going to give you the points, because I don't think that's a valid question. Nobody can read off those kind of diagrams that we've seen any accuracy at all, right? And in fact, I'm not even sure some of my whole numbers are that good, right? I've got a good feeling that I'm probably out as well. So if I was doing that question the way they thought you should do it, I would probably get it wrong as well. So I don't think you've done anything wrong except make sure that you do this part again. And then I'm not writing this as the right answer because I just don't want to spend time doing it. But if that did end up being 370, that's all you're going to write down. And you're going to stick to your guns and let them tell you at the end what they said it is, and then you can figure it out from there.
Okay, thank you.
Okay, so if that's all you need, then bye-bye from you. So, Catherine, where's your guys? Oh, yeah, you're here, Catherine. What was your question? You'll have to hit spacebar, Catherine.
There we go. So mine is from section 7.7.
Right.
And the first question I have, because I've tried to figure this out multiple times, is number 3, using the trapezoid rule to find the midpoint in the Simpsons rule, but it's 0 to pi over 2, then it's square root of 1 plus cosine x.
Whoa, I better say that looks weird.
Yeah, it's
Okay.
like,
That looks weird. So let me see what that looks like. So it's in 7, 7,
yes, number 3.
number 3. So there will be some differences in my 3 and your 3. Oh yeah, I can see it now. Okay, yeah, I know what you're talking about now because I can see it in front of me. So it's 0 to pi upon 2 of a really ugly function called 2 cosine x. And we're being asked to do it to 4 strips. And you're being asked to get a trapezoid, a midpoint, and the Simpson for it, right?
Yes.
Okay. I can show you that one. Let's leave this fella and see what that looks like then. Right, it's this fella. Now, if you imagine this being 0, and you imagine this guy here being pi upon 2, and I don't really care what the curve looks like. Can we pretend that it looks like that? It's just something that I can put pictures into, right? You're going to do 4 strips, so it's going to go 1, 2, 3, 4. So I'm going to set up a table of values so that I can use the trapezoid and the Simpsons rule first, and then we'll do the midpoint after that. Now, you're going to start at 0, right? And then you're going to do 5 points, because 4 strips give you 5 points. The delta x in this question is b take away a over n. So it's pi upon 2 take away nothing divided by 4, which means pi upon 8. So my table is going to go 0, 1/8 pi, 2/8 pi, which is a quarter, 3/8 pi, and 4/8 pi, which is a half. So that's how I'm going to construct the table. I'm then going to get the calculator to figure out what this ugly thing is equal to at each of those points. And they're all going to be weird decimals, so I can live with that. Well, there's a short way of doing it. Let me show you the short way. You go into the calculator and you make sure that you're back in function mode. And then you type in whatever the function is. In this case, it's the square root of 2 plus cosine x. Make sure I'm in radians, which I am. And then you go second table setup, and I'm going to start at 0, and I'm going to go up in pi upon 8s. And then I can just read off the answers. So second table at the end. And that first guy is 1.73. That next one is what pi upon 8 is, so it's 1.71. I'm rounding these off because I don't have a lot of room. 1.65. The next one is 1.54. And the last one is 1.41. So that's how I created the table that I'm going to use to get this fella and this fella. Because once I got this table, it's really just going to be heavy duty plugging and chugging. Did you get that table sorted out, or was that your problem?
I think that was my problem. I put in the wrong numbers.
Okay, so are we cool then how you would do this one and this one? So for instance, in this one, it would be delta x over 2, which would be what? This guy divided by 2, so that's pi over 16. And then it would just be one of these, and then 2 of these, 2 of these, 2 of these, and then finish with one of those. And that's a big ugly calculation, but can you imagine you do it and you get your answer.
Okay.
Now to do Simpsons, it's going to be delta x over 3. And Simpsons is that 14242 thing, right? So that's a little bit messier. 1 of the first guy, 4 of the second guy, 2 of the next guy, 4 of the next guy, and finish with 1 of the last guy. And delta x is this. If you divide this by 3, you get pi over 24. Pi over 24 times whatever that adds up to, and you got your answer. So that's how we would do a trapezium and a Simpson 6. Now, to do a midpoint 6, we have to create a new table, because that's this guy and this guy. If you're going to do the midpoint, don't you use an x value between these two? And here and here and here. So what will that fellow look like? Well, it'll start with x. Halfway between here and here, well, if you add these two up and divide by 2, you find out that the halfway point is that. If you add these two guys up and divide, you get 3/16 pi, 6/16 pi, and am I right with that? Let me double check. 2, 3, yeah, that's good. 3, 5/16 pi, that's better. And 7/16 pi. So if you want to do this fella, you go to your calculator and you just change the setup just a little bit. So you go back into table setup, but you tell it to start at pi divided by 16 instead of 0. And that's all you change. So when you go to second table, those guys are these guys. And then for the midpoint, it's just a delta x, one of everybody from that table. Is that helpful? Do you see essentially? It's really a heavy duty number crunching world. For instance, that first one there is roughly 1.73. The next one is 1.68. The next one is, well, 1.59 rounded up is 1.6. And the last one is 1.48. So the midpoint would be one of these guys, one of these guys, one of these guys, and one of these guys. Delta x is still pi upon 8. So pi upon 8, whatever that comes to, and you got your answer.
Yeah, I think I just set my tables and graph up wrong. And then
Okay.
my other question is number 4 on the same homework section.
Okay, let's see what that looks like. Number 4. Same homework section.
Yes, it's pretty much using the same things, but
Yeah. It is, it's exactly that. It's using the same thing. So in this second question, it's 0 to 4 and n equals 8. So if you do the split, I think everything goes 0, 0.5, 1, 1.5 all the way at the end, right?
Mm-hmm.
So did you do that? Is your start value 0, a half, 1, 1.5 all the way to the end?
I think I did that, yeah.
Okay, so I'll have to set the function up before I disappear from here. And here we go. So see how this works. Right, so I know that delta x is 4 take away 0 divided by 8, right? That's b take away a, and that's where the 0.5 came from. So my table is going to go 0.5, 1, 1.52, 2.5, 3, 3.5, and 4. If you can fill in this table, then aren't you really just going to do this guy?
Yep.
So what we really need to do is be sure that we know what the numbers in the bottom are, because if we get them, we're done. Right. So this table that I'm about to do, this one here, will be able to be used for the TA and the SA, right?
Mhm.
So I could simply do it one at a time. I'll do one of them the slow way, but maybe that'll work, because sometimes there's just too many buttons for you to keep track of. At 0.5, the natural log of 9 plus 0. Plus e to the power of 0.5. Oh, it starts at 0. I don't know why I didn't put that in. It goes 0 to 4, right? I guess I just forgot the first number. So 0 to 4. So as if I hadn't made that mistake, let's do it for 0. It's the natural log of 9 plus e to the power of 0. And the answer is about 2.30. Now, if you wanted 0.5, you would do the natural log of 9 plus e to the power of 0.5, and that would get you 2.37 roughly. But that's a lot of work. So I'm now also going to show you how to do it with the table. You go up here and you type in the natural log guy. So it's natural log a 9 plus e to the power of x. This is just a shortcut to save me in some work. And then set up the table. Now in this question, doesn't the table start at 0? And what they call delta table, that's just their one, that's their name for delta x. So type in nothing 0.5. So start at 0 and delta x is 0.5. And that's that bit done. And then the last part is get the numbers, second table. And there's my 2 point, can you see that 2.37?
Mhm.
Right, so the next one is 2.46. The next one is 2.60. At 2, the answer is 2.79, which rounds off to 2.8. At 2.5, the answer is 3.05. At 3, the answer is 3.37. If you want to see more numbers, you just scroll down. Oops, that's not right. You scroll down. And the next number is, it looks like it's 3.74. And the last number is going to be 4.15. Okay, so if I had this table and I wanted to do T6, it would be delta x over 2 followed by one of these guys, two of these guys, two of these guys, right, all the way to the last one, and the last one you just use them once. And delta x in this case is 0.5, so 0.5 divided by 2 gets you 0.25 times a whole load of stuff, and that would be T6.
That's why I'm messing up. I'm setting my table up totally wrong.
Okay, so I mean, do you feel you can set it up correctly now?
Yes.
Right. So when you're doing the midpoint one, will you remember that you don't use 0 and 0.5, but you use halfway between them? So this is what you'll use. This is the table that you'll start and fill up for the midpoints.
All right.
Okay.
Thank you.
You are welcome. Hi, Douglas. I'm not quite sure what you're doing here. What's up?
Oh, hey. Yeah, I had trouble with number 15 on 5.1.
15, 5.1.
Yeah.
Okay. Might as well do you next. And looks like poor Ripken's going to be last. You don't mind being last, do you?
No.
No, okay, good. God, I'm so easily distracted there. One more time, what was that question? 15, 5-1.
Yep, that's right.
Okay. So let's go home. 5-1. And what number?
I guess the first part, finding the upper and lower sum.
Yeah, but which question?
I'm not sure what I'm understanding here.
Okay. We're in section 5-1. Is it question 7, question 11, question 16?
Oh,
Which question? I lost you. It's at 15?
15, yeah, that's right.
Okay, we're good. That's all I needed to know. So
Okay.
you're almost at the end.
Yeah.
Right. So we got a little funny picture thing going on. That's a little bit different. I don't know if you can see it. Can you see the picture?
I can, yeah.
No, okay. So that means I'll go back out and we can both double check that that's in fact the question. My dog's over here wanting attention. Darn it, I'm so easily distracted. Basic, there we go. It's this one here, right? So it looks something like this, right? So it's 1 plus x squared between -1 and 1. We're going to do it with 3 strips, and then later on we're going to do it with 4. So let's just focus on 3, because if we can do it with 3, you know, you can do it with 4. And they ask for an upper strip and a lower strip. This picture is not relevant to that question. It's relevant to these pictures. So if you're cutting this shape into 3 strips, which one of these 4 pictures would actually represent the way that we would tackle it? And we're interested in essentially what the thing would look like if you drew it. So do you know if it's number 1, 2, bottom left, bottom right? Ah, I can tell you it's got it there. It's bottom right. Can you see it in the picture, right? So we have 2 different pictures superimposed. The ones I'm going to call the dark blue. Do you recognize that the dark blue ones here are using these rectangles?
Yeah.
And that the light blue are using taller rectangles.
Right.
Great. So let's figure out what they're getting at when they talk about an upper sum and a lower sum based on this particular function. So what we need to do here is we need to kind of set up, and that's what I'm doing, although you can't see me right now, set up a table of the values that we're going to use. So it's -1, -1/3, +1/3, and 1. And the reason I know that's the x values, can you see they've written down here at the bottom?
Yep.
Right. So that I'm going to write down, and I'm also going to write down y equals 1 plus x squared. And we're going to leave this guy, and we're going to go to my white screen. And it's this fella here. And for this function, I'm going to evaluate it at these key points. This one I can do easily, this one I can do easily. This one isn't too bad, it's a 9, so it's basically 10/3. And this one is 10/3. And where are we going? That's basically what the curve looked like. And it kind of started here, right? And it finished here. Now, yeah, it kind of sort of looked like that, right? So that was -1, there was -1/3, +1/3, and 1. So far, so good?
Yep.
Right, so let's look at the 2 types of rectangles that we're using. And one of them is going to be called the upper sum. And the answer will go here. And the other one they called the lower sum. So what they're saying is one of these is the overestimate and one's the underestimate. So let's look at the overestimate first. If you use I think they were, oh God, I'm bad at drawing here. Can you pretend that I drew it better? I think they were light blue. Weren't they light blue in the picture? The big rectangles, right. So all I need to do is find the heights of these three guys, right? Multiply them by their width and add them all up, and it goes in here, right? So let's look at this fella here. Would you agree that the height is 2?
Yep.
And would you agree the width is 2/3?
Yep.
So this area is 2 times 2/3. Check. Right, now that middle one is also got a width of 2/3. And would you agree its height is 10/3?
Mm-hmm.
So that is going to be the area of that middle one. Now the one on the right hand side, this fella over here, it's also got a width of 2/3. And oh, isn't its height, I know I've drawn it badly, but isn't its height 2 as well?
Yep.
So if I take all of this and I plug it in my calculator, I will be looking at an upper sum. So let's clear that out. And I'll put it over here. No, you can't. I'll have to move this then. So 2 times bracket 2/3 because plus 10/3 times 2/3 plus 2 times 2/3. And I have an answer of 4.89, I guess, to 2 decimal places. I can't remember if they wanted 2 or 3, but that's what I have. And you see, that would be my upper sum.
Right.
Now, can you imagine I then go back to that same picture, but this is going to be the 3 rectangles that I'm going to use. And I can't remember the middle one, but it's dark blue.
Yeah.
So I don't know what the middle one is, but whatever it is, you will find the heights and widths of those 3 guys. You'll add them all up, and that will be your second answer.
Okay, so yeah, so we're not using all left sides, all right sides.
No,
because...
you're not in this question. That's that's where
Okay.
the confusion is. Actually, I would have preferred they did, because that would have been much more consistent. But I guess what they're doing here is like a one-off method. Hey guys, I can see from this picture that this answer is definitely too big and this answer here is definitely too small, and therefore you can do that upper and lower sum. If I had done left 3 and right 3, do you know I wouldn't have been able to say upper or lower sum?
Yeah.
Because the thing goes down and then it goes up. In fact, I think you get the
that's what I was
same answer.
confused with that.
I think you get the same answer, don't you, if you do the left and right? If you did it that way.
Oh.
I'm guessing that the area in both situations ends up being the same.
Oh yeah, probably.
Right, and so anyway, are we cool?
Yep. Great. Thank you.
You are welcome. Right, looks like, oh, you may have another question, Catherine. No? You're just good, you're watching. Nothing wrong with that.
Learning.
Right, Ripkin, you're the last one in, and then I have to kick you all out because I have to get ready for my next class. So I will keep this video, and it's just going to get tagged on at the end. So if there's anything that you think can't, because I'm going kind of fast, you can watch the video, right? So if something doesn't come up. Okay, what you got?
Is on section 5.2,
Okay, what number?
number 4.
Number 4. Okay, let's have a look at that one. 5.2 home. Come on, there we go. 5.2 number 4. Okay, I'll go back out and in, and we can just verify that it is the question that you're talking about, because it does randomize them a little bit sometimes, in which case questions go wonky. Here we go. I think it's this one. Is it this question here?
Yeah, right. The single integral in the form of, yeah.
Right. So we're being asked to combine the integral from -42 of some function plus the integral from 2 to 3 of some function. And then the sneaky part, take away the integral from -4 to -1 of some function. Is that what it says?
Yep.
Oh,
Or like
that's
some variation, different numbers, but
essentially the same part.
Yep.
I'm a little bit confused about this one. I'm a little bit confused, but here goes. If you combine these two together, won't you get the integral starting at -4 and finishing at 3? Does that seem reasonable?
Are you showing it on the paper or?
I am. Thank you. Let's show you what I'm typing. Right, can you see? Oh, try again. Uh-oh. Well, that took a while. That was strange. Okay, so if you combine these two, so you're going from -42 and then you're continuing a little bit further from 2 to 3, wouldn't that be the same as starting at -4 and finishing at 3? And then we're going to have to figure out what on earth the negative in this bit means. Well, if adding means you combine them together, isn't negative like you're cutting a bit off?
Yes.
And what bit are we cutting off? We're cutting off the bit from -4 to -1. So if you take from -43, but you cut off the -4 to -1 bit, aren't you only left with the bit that starts at -1 and finishes at 3?
Oh, okay.
And that's it.
Okay. Because when I was trying to watch the video, they were doing this weird stuff that I'd never seen before, and I just wasn't getting it. So
Are we getting it now?
yeah, I'm getting it now though.
Right. I don't know what the videos
Yeah.
like. They're not my videos. They're just other people's videos.
Yeah.
So other people don't always describe things the same as, not everyone's the same, right? So,
Yeah.
we cool now?
Yeah.
Are we anything else, or are we out of here?
I have one more thing because
Okay, what you got?
This is for your the statistics class.
Um,
No, it's just like a time frame. I have
okay.
work coming up. It starts at like 2:30.
Mm-hmm.
Class is at 2:24. So
Right.
I might leave around 2-ish, if that's okay.
Yeah. So you're going to miss the last 20 or so minutes?
Yeah, or so, yeah.
Okay.
I'll watch the videos to get the last 20 minutes.
Makes sense. Okay.
So,
Is it just a one-off, in which case it's not a big deal?
because the school didn't give me the time frame to of when the class was starting. My work goes out 4 weeks in advance when it comes to scheduling. So now I'm gonna have like I think it's only 2 weeks of. I think it's this week and the next week. That's about it.
Okay, that's a bit. Yeah. If you can be really nice and ask your boss to shift it, it would be great.
Okay. I think I can get.
It's just you're going to lose a lot of different bits, and you might not always pick everything up.
Yeah.
And just try to make sure that you get the right opportunity to see things.
I want to go in today and see if I can get next.
Can I just come half an hour later? I don't know if that's possible. It might not be, and I understand that. But if it is, it would probably help.
Yeah, that's what I'm going to ask them.
Yeah, you can only ask, right?
Yeah.
They can only say no.
Yeah.
That's it. That's the end of it. Okay, well, I'm out of here then. I have other stuff. This conversation will be cut out of the video. Nobody needs to know about it, right?
Okay.
So don't be surprised about that. But everything else, if you don't mind, I can keep it so other people can see examples. Okay, thank you.
Good. Yep.
Right, then bye-bye.
Bye.